Okay, so welcome everyone to our July 2024 First Fridays with Professor Jim Woodhouse. Um, so recently, he's been heading a group doing some research into the bridge and its effects on the tuning the response of a violin. So he's here to give a preliminary report on the results. Jim?
Okay, thank you. Let's press the sharing button. And so, yes, indeed, the origin of this work. Well, some years ago now, I did a bit of work on what a violin bridge might do, and I hadn't really thought about it anymore. But about 6 months ago, the sort of Oberlin organizing bunch were having a discussion about what they wanted to do as a research focus this year. And Joseph Curtin was particularly keen to follow up that old work on the bridge and go into more detail and bring it a bit closer to the violin maker's bench. So I've been doing a bit of stuff, and then a few weeks back, we had a small group gathered in Cambridge for a few days, and we had a rather intensive few days doing various tests revolving around the bridge. And as Fan says, this is still work in progress, but this will be an interim report of the story so far. So this is, roughly speaking, the title. How much, as a maker, how much can you expect to change by making adjustments to the bridge? So here's a scene from the gathering in Cambridge. It's the room I'm sitting in now, but a bit of it that you can't see in the video image. Some familiar, here's the back of Joseph's head. Colin Goff, Luca, Andreas Hudelmeier, Sean Hardesty. There were a couple of others who aren't in the room when I took this particular picture, but you get the impression. So, bridges. So what does a violin bridge do? Well, this is my view. Everything, the physicist's view always tries to simplify things as much as possible. So lots of things that I will say, I hope they're all approximately true. And I'm not really claiming that anything is more than approximately true. Filling in the details and making things really quantitative is why this is still work in progress. We're trying to tighten that up. So here's a violin bridge, as you will recognize. Here are the 4 string notches. When you bow a string, you have to get your bow obviously into an angle where it doesn't hit the other strings. And then the fluctuating force from the vibrating string on the bridge is mainly in the direction of bowing. So the 4 strings produce forces like these red arrows that you see here. And now they're all, roughly speaking, horizontal. And so in themselves, they'd be very badly oriented for making the violin body vibrate, because that needs to be moving in the vertical direction. So that's why you have to put up with this inconvenient high bridge on the violin, or all the bowed instruments, nearly all the Western bowed instruments, because this high bridge can convert these lateral forces at the top into more or less vertical forces at the bridge feet, which then act on the violin body. So that's the bridge's main job, is to convert forces in this direction from the red arrows into forces like the green arrows. Those then act on the violin body, and the bridge feet are pretty small, so as a first shot, we can say that these forces act at just 2 points on the violin body. And of course, those forces make the woodwork vibrate, and the vibrating woodwork results in sound radiation. And there you are, for better or for worse, with the sound of a violin. So, the bridge itself is fairly simple. It's got these sort of detailed shapes that you're all familiar with. I didn't say decorative shapes because all these cutouts do play a role in the story that we're looking at here. But we're talking about acoustics here. So does the bridge in itself have resonances in the audio range in the plane of the bridge, which is, remember that that's all the forces that I was talking about in the previous slide are in this plane. And a typical violin bridge has two resonances in that range. Around about 3 kilohertz, it has a rocking resonance where, roughly speaking, the top of the bridge rocks from side to side, flexing this relatively thin woodwork around the heart and the cutouts. And mechanically, we can kind of represent that by the sketch that's superimposed here. So we've got a kind of bar with a weight on it. It's pivoted at this red dot here. And then it's got an old-fashioned clock spring shown in red here, which is a torsional spring. And so we've got an inertia and a spring, and those are the two ingredients you need to make a resonance. So we can, and any resonance, any single resonance of any mechanical system can be approximated with something involving masses and springs. So we got this rocking resonance around about 3 kilohertz. And then if we look a little higher up in frequency, there's a bouncing vertical resonance, which we can idealize as this mass blob here sitting on a red spring centered on the base of the bridge and just bouncing up and down. So roughly speaking, the top bit of the bridge probably moves pretty much as a rigid body. And there's some flexing, probably mainly through these thigh parts of the bridge legs. Again, that forms a spring. There's a certain amount of mass. A mass and a spring together make a resonance. Okay, so having said the bridge itself is quite simple, but its effect is not so simple. The main effect of these bridge resonances is a rather subtle thing. I've talked about it before, and I'm sure a lot of you know about this, but it's important for this talk to tell you again. So here's a typical frequency response function of a violin body. It's the particular response that's called the bridge admittance. Again, a lot of you will know what that looks like, but just for those who don't, here's a picture of a bridge admittance being measured. So this little impulse hammer is tapping the bridge on one corner, approximately in the direction of bowing on the nearest string, the G string. And then we're observing the motion actually at the other corner. You can't quite see how, unless you can see a very faint red spot here. So out of shot on the right-hand side, there is a laser. It's reflecting off a bit of reflective tape on this corner of the bridge, and clever stuff in the laser system using the Doppler effect allows us to get a signal proportional to the velocity of the motion of the bridge in response to this impulse. We gather those signals in the computer, we do a bit of stuff with the FFT, and we can get this, this frequency response here. Now, there are all kinds of interesting details in this, most of which I'm not going to talk about today. At low frequency, as with pretty much any vibrating system, we have a few peaks that are quite well separated from each other. Each peak corresponds to a particular vibration mode of the violin body, including the bridge. And these ones that I've arrowed are three of the ones that we often call the signature modes. This one down here is the air resonance, 280 or so hertz. This one is probably CBR. It doesn't matter what they are. there are some individual resonances at low frequency. At high frequency, things are more complicated. The first thing that you see is a whole forest of peaks and dips caused by all the many resonances of the violin body, including the air inside it. That's part of the violin body. The important thing for our present purpose is there's a kind of hill in the forest. This green dashed line, something usually called the bridge hill. And I'm not going to talk about how it does it in this talk, because there are more interesting and new things to talk about. But you'll see the gist of that as we go on. This without the high bridge with the cutouts and those resonances, we would still have a forest of little peaks from the body resonance, but the trend of them would just be a horizontal line, would not have this green dashed hill in it. So that's caused by the bridge in conjunction with the part of the violin body that the bridge sits on, often called the island area, the bit between the F's. And bridge adjustment can modify this hill. And that's what this story is all about. What exactly? How can you modify it? How much can you expect to change? And various questions of that kind. So that's our topic. But always we're looking at a kind of hill feature lying underneath a forest of detailed peaks. And I'm not going to say anything about the detailed peaks, just the hill. So back to this picture of the idealized versions of the two resonances. And the important thing here is just to count up how many parameters we need to characterize these. So for this version of the rocking resonance, we need to know the stiffness of this spring and the amount of inertia associated with this pivoted bar. So something called moment of inertia. We can combine those two things to predict the rocking frequency. Well, what I mean by that in here is the frequency you'd get if you clamp the feet of the bridge in a vise. We'll see that in a second. Once the bridge is on the violin, it does something more complicated, which we will come to. So you need, you need two parameters, a frequency and a moment of inertia, but you also need a third one, because you need to know the length of this pivoted bar from the top of the bridge, or shall we say, if we're bowing the middle strings, down to this pivot point. Well, what does that pivot point represent? Well, that's a good question. It's purely schematic in this diagram. The actual motion in this mode has the top bit of the bridge moving more or less rigidly. But then in this middle area where there are various thinnish parts, there's some kind of complicated flexing. What I'm representing by this pivot point here is the effective center of rotation of that rigid top part of the bridge. And maybe it's around about where I've put the dot, but it's actually difficult to guess in any detail. We'll come back to that in a moment. The effect of this resonance is also affected by the foot spacing, which is indeed a sensitive parameter, but I'm not going to vary the foot spacing in this talk. So for that purpose, all the bridges we will look at have got the same foot spacing. So to characterize this mode, we need three parameters. The bouncing mode, the vertical mode, is simpler. It only needs two parameters. It needs the mass of the mass and the stiffness of the spring. The ratio of those tells you the resonant frequency, the bouncing frequency. I say usually around about 6 kilohertz. So 3 parameters for the one on the left, 2 for the one on the right. So a combined bridge model capturing these things has got 5 parameters. Now, in principle, you can estimate some of those parameters. In fact, if you work hard enough, you can estimate all of them directly. So here's Andreas Hödelmeier in the workshop. Now, regulars in this talk series may remember Andreas gave us a talk a year or so ago about a cunning trick that he uses where he clamps a bridge in a vise, and you can see it very small. There's a bridge in the blue thing is his vise. His vise is held in my red vise for the purpose of measurements, but none of that is relevant. There's a bridge held in a vise. If you tap it on a corner, you can try to detect the rocking frequency. You might do that just with a frequency app in your phone, or you could do it as a more laboratory-ish measurement. If you tap vertically on the bridge while it's in the same vise, you can excite the bouncing resonance and capture that frequency. So we could measure directly the two frequencies, rocking and bouncing. Andreas then had a cunning trick where he measured those frequencies on the bridge as it stands, and then he attached a small mass to the top of the bridge of a known, which he'd weighed, you know, so he knows what the mass. That shifts the two frequencies downwards, and by doing a little calculation with the frequencies before and after, you can back out a version of the effective mass of these vibration modes. So you've got 4 of the 5 parameters in principle from that. However, in principle is the right for the moment. At the moment, there are still some puzzles associated with making that work. It works perfectly well in principle, but there are several different ways you can estimate these parameters, and they all give roughly the same answer, but not quite exactly the same answer, and I'm still trying to track down just exactly what is causing that disparity. So I'm going to gloss over that. I'm going to concentrate on things we can do by measuring the bridge on the instrument with the strings, so that in the normal state. And as we'll see in a moment, if we do 3 sets of measurements on the violin in various states, we can capture, at least approximately, all the information we need to put together with the bridge model that I talked about earlier. So we measure the bridge admittance, the rocking direction, and the same thing in the vertical direction. So we measure 2 admittances on the bridge, on the strung violin, with the strings damped usually, but that's not relevant for this discussion. Then you take the bridge off and you look at the 2 places where the bridge feet are going to sit, and now they're not there. We do a mechanical measurement, you'll see a picture of that in a second, at the 2 bridge foot positions. So basically we stick 2 small accelerometers on the bridge foot positions, and then we tap with our little impulse hammer on top of the 2 things, and we measure those admittances. And at the same time as we're doing that, if we've got a microphone in some standardized position, or Joseph Curtin's circle of microphones, whatever, we can measure the sound that's radiated when the body is tapped at the bass bridge foot position and separately at the treble bridge foot position. So we do those 3 sets of measurements and we can stir them together. Here are a few pictures of those measurements being done. Again, this is the chair I'm sitting in as we speak. This is the table behind me, is the one you see in the picture. So here's a violin, you probably knew that, held in a convenient holding fixture with the strings damped. And here's a close-up of that. This is during a measurement of the vertical admittance. The bright red spot is from the laser beam, and in this left-hand picture, this is the laser unit that's firing a laser beam at the bridge. Here's the little impulse hammer, tapping as close as I can get to the red spot, but without getting in the way of the laser beam. So we do that measurement grab the signals into the computer and do stuff, and we can get the vertical admittance. We can do the rocking one that you saw a picture of earlier. Then we take the bridge off, leaving the violin in the state you see in this picture. And you either take it off completely, or you can just about get away with gathering the strings out of the way as long as nothing buzzes. And then these are two small accelerometers stuck to the body at the positions of the bridge feet. And here's the little impulse hammer tapping on top of one of those accelerometers. And again, you gather the response from both, and then you move the hammer over to the other side. And then out of shot, at the same time as these taps are being done, there's a microphone recording the sound from tapping at those same two places. So we collect those things. And as you'll see progressively during this talk, we can do almost everything we might want to do by putting those measurements together. Now, the first thing to do is to check if my simplified model of the bridge modes really works. So what we can do is, remember, we've measured the admittance, the two admittances on the bridge. We've also measured the body vibration behavior without the bridge at the bridge foot positions. And then we've got this simplified theoretical model for the bridge with these 5 parameters. So we can ask the computer, I suppose if I was being fashionable, this is not AI, but I suppose it's getting close to it. This is AI bridge adjustment. We can say, we can ask the computer, can you choose values of those 5 parameters such that the theoretical prediction is based on the measured response of the body at the feet combined with the theoretical model of the bridge modes. That can be used to produce predictions of both the rocking and the bouncing admittance. We can compare those with the measurements we've got of both, and then say, can we choose parameters such that those agree? And here is an example suggesting that at least on a good day, we can. So on the left, we've got the rocking case. The red curve is the measured admittance. It's exactly the same one that you saw a few slides back. The blue curve is the computer's best shot at fitting to that, using the measured behavior of the violin, but the theoretical model of the bridge.
Can I just ask, the theoretical model has parameters, and you're fitting for those parameters in situ rather than the numbers you measured with the bridge isolated?
Yes, yeah, absolutely.
I anticipate to be quite wrong, because the strings and the soundboard contribute to those.
Well, that's not the soundboard. The effect of the soundboard is...
Oh, because it's not... Yeah, I got a banjo, which is different. The soundboard's not moving relative to the bridge.
Well, the coupling to the soundboard is included in the model via this measurement at the bridge feet positions. So that coupling is fully there. I am ignoring the strings. Ask me that at the end.
Okay, I'll be quiet.
It works. Well, we achieve a rather satisfactory fit. So this is the same comparison for the vertical admittance. Again, the red curve is the measurement. The blue curve is the fit. And so these are 2 fits using the same parameters in the bridge model, just simulating the 2 measurements by applying the force and observing the motion in 2 different places. And the left hand and the right hand wiggly curves look quite different, and we can fit both of them reasonably well. At the bottom of the 2 plots is some indication of how well the fitting process works. So this is a contour map. So we've got values of the rocking frequency here and values of the rocking moment of inertia up here, the numbers don't matter. This is, so I've simply computed my model for a grid of points here and just taken the deviation between the blue curve and the red curve, the RMS deviation between those, exactly as you see them here in decibels and with a logarithmic frequency scale. And then this is a contour map of that deviation. And the contours are 0.5 dB apart. The red star is the optimum, the best fit that the computer gave. And you can see this is a contour map of a hole in the ground. So where there's a hollow here and a minimum in the middle. Here's the corresponding contour map for the bouncing mode. We've got the bouncing frequency and the mass for the bouncing motion. And again, the red star is the best fit and the contours are 0.5 dB apart. That's all fine, except that with this left-hand one, I've cheated slightly because remember I said that there are 3 parameters. I'm only showing 2 of them here. So I'm just going to give you a glimpse of it's not so easy to do easy plots with 3 parameters, but here is the space. So the contour plot you saw on the previous slide was a horizontal slice through this at the best fit position. Now the stars, the colors show how good the fit is roughly. So red is best, blue is 0.5 dB less good, black is 0.5 dB less good again. So the fit, that's enough, that'll make you giddy. Here's a still of the same thing, just so we can look at it without going round. So all 3 parameters make a difference and they're connected together. This blob here is slanting in the diagram. So what I was showing in the contour map, which I'll show again in a second, is a horizontal slice through this, through the best fit point, which is somewhere in the middle of these red points here. But there's more. In this area is the question of getting quantitative agreement with the clamped bridge foot measurements, which I'm not going to talk about. So that's just back to these contour maps, because I'll be showing other examples of these 2 contour maps, just bearing in mind that there is a 3rd dimension of the rocking one. Now, what I deduce first of all is a measure of relief here. We've achieved a reasonably convincing fit of the model to the measurements here. Not perfect, and there are many reasons why things would not be perfect, but it's not bad. It's close enough that it encourages me to think that this simplified bridge model is probably capturing the main effect of the bridge. In particular, this bridge hill is captured rather reliably. So this is the rocking measurements, and mainly you see a hill based around the rocking resonance of the bridge. In the one on the right-hand side, you see a hump up around 5 kilohertz, and that's something to do with bouncing rather than rocking. So the 2 hills based on these 2 resonances. So the model can work, and so let's just think about some of the questions we might want to use it to inquire into. So one question we might ask is, how much do different bridges actually vary? A question from the workbench, what's the biggest change you might realistically be able to make by modifying the bridge? In particular, can you make a big enough change to fix the problem that the violin owner is complaining about? So far, I've only been showing results based on the bridge admittance, which is a mechanical measurement. Can we say something about the effects of bridge adjustment on the sound that's radiated to a listener? Once we've said something about that, then we can ask, how much do you have to change those bridge model parameters in order that the effect is audible? So what's the smallest adjustment you can do to a bridge where such that we would predict that you can hear the result? And then finally, or at least finally for this list, I think a lot of makers are firmly of the view that some violins are more sensitive to bridge adjustment than others are. Maybe this model could tell us something about how much violins might vary in their response to bridge adjustments. So those are 5 interesting questions. I'll say something about all 5 of those in the course of this talk without giving you a final definitive answer to any of them, needless to say. So here's an experiment with different bridges. Now, these are 3 bridges that I happen to have left over from the earlier study 20 years ago, whenever it was. Those with sharp eyes will see that these are these bridges for amateurs that have got the tilting feet. That's not just chosen because I'm not good at fitting bridges. It's because I wanted to use the same set of bridges and put them on different violins to see what effect they had. I'll only show the results here on one violin, but these tilting foot bridges do allow you to do that. So these started as nominally identical blanks from the supplier. The middle one has been adjusted into a fairly normal state, maybe a little heavier than some of you would do. The top one is significantly lighter, 1.5 grams instead of 2.4. You can see that I've cut some extraneous stuff off. You can't really see in the picture, but the top part of the bridge is much, much thinner than the usual. So I've took away as much mass, starting with a conventional maple bridge blank, that I felt I could still put regular string tension on so the violin could be played. So there's a light one, a medium one. The bottom one, you can see there's something funny about it. This is essentially an unaltered bridge blank, except that I've filled in the cutouts, because when you buy them, they've already got these cutouts. I wanted to shift these frequencies up, so I filled them in with epoxy. Of course, that's made the bridge a bit heavier, but it should also have made it much stiffer. So a light, a standard-ish, and a heavy bridge, all installed in turn on the same violin, the same one we saw earlier. Here are the rocking admittances, and everyone is just like the plot you saw earlier. The red curve is the measurement, the blue one is the fit using the model, and then underneath it you see the contour map, which reveals something about the rocking frequency and the moment of inertia, essentially the mass of the top of the bridge. So here is the light bridge, the medium one, and the heavy one. And you can certainly see that those admittances look significantly different. There's 50 dBs on this vertical scale here. So between this one and this one, we've gone down by 15 dBs or so at the higher frequencies, and the medium bridge is in between, much as you'd expect. This is all rocking. The light bridge, we've fitted a certain rocking frequency with a relatively low value of the moment of inertia. The medium bridge has got a somewhat similar rocking frequency, but it's heavier. That's the fit is agreeing with what we would have expected. The heaviest one, the contours go off the edge of the graph. So the red star is the lowest value within the range that I've chosen to search. But of course, this is the bridge where I filled in the cutouts. So we can't really do a rocking resonance in the usual sense. And actually this plot is showing what you would expect to happen then. The rocking frequency should be regarded as in inverted commas here, and it's presumably very high. It's off the picture on the right-hand side. The bridge is heavy. We knew it was heavy. So, and what we see here is instead of getting a hollow and a clear-cut minimum in the range, the contours, the best fitting contour simply runs off the graph at this side, and there's quite a large blank area. And that's telling us something which makes physical sense. This is saying that any bridge which has a high enough rocking frequency and roughly the right high-ish moment of inertia produces a fit that's about equally good. Remember, these are half dB apart. So everywhere in this big blank white area, there's virtually no difference in the disagreement. What that is saying is that the properties of the bridge, the rocking frequency property, is not mattering, as it just needs to be high enough, and the real thing is higher than this. There is still a hill here, but the frequency of the hill is not now governed to any extent by the bridge flexing. It's governed by the mass of the bridge is still mattering, and there is rocking still going on, but the rocking is taking place by the top of the violin moving. There's rocking motion of this island area between the F holes. And in this case, the bridge is more or less rigid, and the rocking is just carrying the bridge along more or less as a rigid body. That is plausible enough. Now, next slide, this is exactly the same comparison for the three bridges in the vertical direction. So again, in red, you've got the three measured vertical admittances, and in blue, you've got the model fit. And again, you can see that the three admittances are quite different, and that we've achieved a moderately credible fit to all of them. In the case of the lightest bridge, we get a relatively clear-cut minimum within the range, and then the fit gets less good, whether you move to the left or to the right of that. On the medium bridge, which is a fairly normal bridge, we've got closely spaced contours in the bottom corner, bottom left-hand corner, but the contours get very widely spaced out here. And that's beginning to say the thing that I just talked about on the previous slide, that the bridge bouncing properties are ceasing to matter very much, because there is still bouncing going on, but it's mainly the island area of the violin which is moving rather than the bridge distorting. And by the time we go to the right-hand one and the bridge with its cutouts filled in, the whole top part of the diagram is just one big blank white area. You can have any combination of mass and bouncing frequency in that range, and you get an equally good fit to the measurements. The actual behavior of the bridge on the violin in this vertical direction becomes independent, almost independent of the bridge properties, provided it is stiff enough and heavy enough that you're up into this white region. So bridges, these are quite extremely different bridges, but this is showing that bridges can vary by quite a lot, and at least if we look at the admittance, we can match them reasonably well. So the next, or a little further down my list, was, can we use this argument to say something about the sound of the violin? You don't listen to the bridge admittance. It is important to the player because it has influence on playability, but that's another story. How do we make sounds? Well, here's a picture we saw earlier. We've got the forces from the vibrating strings at the top of the bridge. Those are generating forces at the violin body. And the bridge model that we've now seen working reasonably well, I've used it so far to compute the admittance at the top of the bridge, but the model can also tell us the transfer function from the forces up here to the forces down here. So we can use the model which we fitted by looking at the admittances to predict what these forces on the violin body are. Now is the time to remember the third measurement. And I said there were 3 types of measurement we need to do. We've used 2 of them. We've used the admittance on the top of the bridge, and we've used the body response without the bridge at the feet. I said you should also measure the sound to your chosen microphone position when you tap at the bridge feet. So we've got direct measurements which tell us how to convert these green arrows, forces on the violin body, to sound at a particular microphone position. And the significance of that is that if you're then looking at bridge adjustment, you're not changing the violin body, you're only changing the bridge. So those transfer functions that turn the foot forces into sound stay the same. Bridge tuning, bridge adjustment just changes the properties of the bridge model. So what that means is that we can create something quite interesting. We can combine, so we can take the string force from real playing. I'll show in a moment what that is like. We can use the bridge model with parameters that we fitted to convert those string forces from playing on the G string, shall we say, into waveforms of forces at the 2 feet. Then we can stir those foot forces in with these measured microphone responses and simply add the 2 feet together, and we should get a simulation of the sound of the violin as recorded, as bowed with that particular playing, with that particular bridge, with the properties we've fitted and measured at the particular microphone position that we've chosen. So let's listen to something. So here's how you measure string forces at the bridge. This is a violin bridge where under each string notch, there's a cunning force sensor. The details don't really matter. These are piezoelectric crystals wired together in such a way that they give out an electrical signal proportional to those forces from these red arrows here, forces in the bowing direction. The bridge that they come out on these wires here and get grabbed. So that means you can take a real violinist. The snatch I'm about to play you is played by a violinist called Keir Gogwilt. And the bridge has got all 4 sensors, but it's convenient for this exercise to stick with something that's only on 1 string, because otherwise we need to mix several different bridge responses together, and it just makes things more complicated without telling you anything new. So the little extract of sound that you're going to be hearing several times is a familiar snatch from the Tchaikovsky violin concerto, played entirely on the G string. So I'm going to play you a sequence of sounds. First, let me play you directly the string force signal as it is recorded. I hope that came through all right. Perfectly obviously a violin sound. Not a very interesting violin, not one that you would want to sell probably. This is a kind of physicist's electric violin. We've not done any kind of audio processing tricks to make it sound better. That's exactly what we don't want here. I want to know the actual force applied by that G string at the string notch. So we can take that, a little bit of real playing, and then go through the stages that I've just described. Now I'm going to describe the next 3 slides so that I can go through them without talking in between, because you're going to hear three things, all based on the sound you've just heard. So we take the force at the G string, we calculate the force through the bass foot of the bridge, the force through the treble foot of the bridge. Separately, those generate sound at our microphone position, and then the actual sound is simply given by adding those two things together. So I'm going to play you those three things in sequence. The sound of the, I think it's the treble foot that comes first, the words will say. So the sound of the treble bridge foot only, then the sound of the bass bridge foot only, and then the sound of adding those together to give our best shot at the actual sound of the violin. Now, so I'm not going to talk, I'm going to go through the three things. So I hope those came through. I was really surprised when I first heard those at just how different the bass foot and the treble foot are. I suppose I shouldn't have been surprised. The treble foot, it sounds plausible, but has more treble. The bass foot has more bass. The main reason for that is, of course, that the treble foot of the bridge is sitting very close to the sound post. And at low frequencies, the sound post is rather stiff. So that force doesn't get turned into all that much vibration at low frequencies. At higher frequencies, there's plenty of vibration. And that's what you heard. You heard a very thin, the characteristic sound of the Suzuki class with quarter-sized violins, probably. The bass foot is more bassy. The combined sound is more like the bass foot than the treble foot, but actually it is different from either. It's got more bite than either. So that's quite promising. We can make, it may not be, it's not, of course, the same as the sound you would hear if you were standing in the room while the violinist played. Because this is the sound at a single microphone position. When you're there in the room, you've got two ears. So you sample the sound at two positions, maybe you move your head around. So you get a richer source of information on the actual violin play. The sound, the way to visualize, or one way to think about the sound of a single microphone recording is to think of listening at the keyhole while someone plays the violin inside a room when you're outside it. You're listening to sound that's just sampled at one point, and the experience is less rich. You can't cope with the room acoustics so well, and so on. So, armed with that, then, we can, all moderately encouraging, so we can use our bridge model to do kind of virtual bridge adjustment. We can take a real violin body with its measured vibration response and its measured sound radiation. We can take a bridge. We start with this red plot in the middle. These are all pictures of the bridge admittance again. The red curve in the middle is the one you've seen before several times now. So that's this particular violin with the particular bridge that it has on it. We saw earlier that I'd fitted my model parameters to that bridge. So actually, this isn't the measured red curve, it's the blue curve you saw before. The red curve here is the model fit using the parameters which gave a decent fit to the measurement. So this is an admittance which is synthesized using a combination of measured properties of the violin body and the simple 5-parameter model of the bridge. Well, having fitted those parameter values, of course, I can vary them and see what happens. And that's what you see here is a kind of ring around. I've just varied 2 of the parameters, which are the ones that relate to rocking. So everything in red has the original rocking frequency as measured. Everything in blue has a rocking frequency that's 30% lower. Everything in black has a rocking frequency that's 30% higher. So that's the 3 columns of this 3x3 grid here. The rows correspond to different bridge mass. The middle row is with the actual moment of inertia of the bridge. And again, the top one is, I get it the right way around, 30% lighter, and the bottom one is 30% heavier. 30% are quite big variations, but that's meant to show the point. Now, you can see that these curves are different, but it's pretty difficult to compare details. So I've done something to help here. So there's a trick we can do in the computer, which creates the smooth curves. It says in the caption that they're dashed lines, but that's complete nonsense. They're not dashed lines. They're just smooth curves through the middle of the jagged curves. And that averaging process smears out the forest of peaks due to the body resonance, but leaves the bridge hill, the smooth behavior, visible. So I call it a skeleton curve. And remember, it's this bridge hill that we're expecting to be able to affect by bridge adjustment. So each of these 9 plots has got one of these skeleton curves. And now this plot puts those 9 skeleton curves together. Now, if you committed the previous slide to memory, the colors and line types are the same. Let me just remind you. Colors go with rocking frequency. Red is the nominal, blue is lower. Line types, solid lines, go with the nominal mass. Dashed lines go with lower mass. Dashed dot lines go with higher mass. So those are the 9 lines that you see here. We're not going to follow all the details. All I want to draw your attention to is that there's quite a big range here. And admittedly, 30% changes. That's quite a drastic bit of bridge adjustment. But even so, from top to bottom here, we've got 15 decibels at some frequency, really quite big changes in admittance. And each individual one to its neighboring one is 5 dBs, typically in some places. So no surprise to the violin makers in the audience. Yes, you can make a difference to things by bridge adjustment, but this is virtual bridge adjustment. This is 9 different bridges as they ought to behave according to the theory when fitted to the same violin. So that's admittance, but really, we'd like to say, what does bridge adjustment do for the radiated sound? So for that, we don't want to look at admittance. We want to look at these transfer functions. Now, I talked about these before, but I didn't show you a picture of them. The red curve here is the transfer function, frequency response function, from force applied at the G string in the bowing direction to force going through the bass foot of the bridge. The blue curve is the same thing for the treble foot of the bridge. So these are these 2 force-to-force transfer functions. So they don't need any units. They're a force divided by a force. And they don't look anything like the admittance, but they have features in them. And we'll see in a moment how those features change when we vary the bridge. Now, remember something I said earlier. These transfer functions should capture everything that the bridge contributes to the sound from bridge adjustment, because from here, once you know these forces at the feet, the sound radiation by that particular violin body driven at those particular foot positions stays the same when you adjust the bridge. So if we adjust the bridge, these transfer functions should capture the differences in these transfer functions should capture directly differences in the sound. But they have the virtue that we can understand them. We avoid all the complications of room acoustics and what have you, which are there if we actually look at the transfer functions to sound. So that's my violin with its actual bridge. Not as measured. This is rather difficult to measure. That's a story in itself. We have tried. I've seen results good enough to convince me that this theory is more or less correct, but not agreeing as nicely as the admittances do. So this is a prediction from the model. And remember, the model has been fitted to the measured admittances. So there are reasons to believe that the model of the bridge with these parameter values should be fairly good. So remember where we were in the previous slide. I did this ring around of 9 cases of bridge adjustment. Here we did it with admittance. Now here's exactly the same thing applied to these bridge foot force transfer functions. So again, same arrangement. The middle one is the nominal, the same one you saw bigger in the previous slide. This has got a lower rocking frequency. This column has got a higher rocking frequency and so on, lower mass, higher mass. Every one of these curves has got a smooth skeleton curve through it. It's really difficult to look at complicated pictures like this and see what the differences are. So just as I did before, here's the result of combining the 9 skeleton curves, but I've done it separately for the bass foot and the treble foot. So and remember, the solid red line is the actual bridge on the actual violin. Everything else is virtual bridge adjustment. Bass foot and treble foot looking significantly different. Something you can see in here rather clearly is something that I mentioned earlier. You can see particularly clearly in the bass foot, all these curves have some kind of hill around about 2 kilohertz, which is the standard bridge hill associated with rocking of the bridge plus the island. And then very clearly these show up a second hill visible in most of the pictures, most obviously visible in the black one. And that's centered around about 4 to 5 kilohertz. And that's this vertical hill, which is mainly based around bouncing behavior of the bridge plus the island area. In the bass foot, both of those are about equally prominent. In the treble foot, the rocking one is more prominent and the bouncing one is somewhat less so. This isn't the moment probably to try to second guess what exactly is the physics behind all of these things, but there's a lot of information in here. What I suspect most of you want to know is, what does this sound like? So let's turn straight to that. So here is the same picture we just saw, the 9 cases. I've chosen 2 of the cases. They're the 2 which have got the actual bridge mass, but a reduced rocking frequency and an increased rocking frequency. What I'm plotting here is the transfer functions to the foot forces, but we already heard some sound examples where we combine those with the sound radiation behavior of the violin and turn them into sounds. So I'm going to play you first the left, the 2 things with the green circle. So you're going to hear the same snatch of synthesized violin music with two different values of the rocking frequency of the bridge. Now, I don't know how different those sounded for you. That will depend on your audio quality. But they are quite clearly different, which is a relief because this is quite a big bridge adjustment. And they're just an example. We can generate sounds like that for all the cases here, but you soon run into listening fatigue if I try playing you too many of them. This gives us a tool for hearing the virtual effects of bridge adjustment to a reasonable approximation. Now, on to the next question, the final question on my list of 5 questions. I said, can we say something about the sensitivity of different violins to bridge adjustment? So I'm going to show, let me just go back here. For the purpose of example, I'm going to use the same 2 cases marked by these green circles here. So relative to a nominal case, 30% reduced rocking frequency and 30% increased rocking frequency. Sorry about that. Now then, so this is for those 2 cases. So the red curve shows the difference in dBs. Now this, I don't know if you can't read the number, this vertical scale only runs from -10 dBs to +10 dBs. So it's a fairly tight range. The red curve shows the difference between the modified bridge and the original bridge, the difference in the sound level expressed in decibels. So what this is showing is that by reducing the rocking frequency, you make it louder in this frequency range, and you make it quieter here. The decibels have gone negative. If we increase the rocking frequency, that's the blue curve, and you get approximately the same curve upside down. Increasing the rocking frequency makes it louder because you've pushed the rocking frequency up. But so quieter at lower frequencies, louder at high frequencies. So that's a kind of graphical view of the predicted effect of 2 particular bridge adjustments on the sound of one particular violin. And because I know someone is going to ask this later, this is an amateur-made violin made by me in 1990, so it's fairly mature now, but it's not bad, but it's not professional grade. Now I've got the same results for 2 other violins, which are just 2 that we happen to have that full set of measurements for. I've done the same in each case. I've done the 3 sets of measurements on each violin. I've taken the bridge that the maker fitted to it and extracted the parameters for my bridge model. And then I've changed the rocking frequency up and down by 30%. So I've only done this full set of measurements on 3 violins. So this is the sum total of the world's data on this subject at the moment. The middle plot is a violin that one of the violins that Andreas Hudelmeier brought along to our workshop in Cambridge, and a complicated story, but he wanted to do a bridge experiment, so he wanted to have 2 contrasting violins. So as I understand it, he got 2 Chinese violins, but then he took them apart and tweaked them so that one of them, this one is the thinner, lighter of the 2. And it happens to be the one that we did a lot of our measurements on, and with one of the bridges from his collection. The right-hand plot is one of Joseph Curtin's ultralight violins, which also has an ultralight bridge. So here we got 3 different violins with the same virtual bridge adjustment being made to all of them. Not the same bridges fitted to all of them, but in each case I've started from the bridge that was actually on the violin and then said what would happen if we increased and decreased the rocking frequency. You can see that the broad pattern is pretty similar. The red curve always goes up and then down. The blue curve always goes down and then up. And they cross over around about 4-ish kilohertz. But they're certainly not the same. And for this particular thing, my violin, this red curve goes up to levels like 5 dBs. Andreas's goes up to levels like 3 or 4 dBs. Joseph goes up to levels more like 2 dBs mostly. So in terms of this particular bridge variation, changing the rocking frequency, it rather looks as if my violin is more sensitive to changes. Andreas is in the middle and Joseph's is less sensitive to changes. However, this is, remember, our model has got 5 parameters. This is only one of them. I'm going to show you some data for the other 4, but I'm not going to try to squeeze all 3 cases. I'm just going to show my violin versus Joseph's as the extreme case. So here is the same thing, varying the rocking inertia of the bridge. So that's making the top of the bridge heavier or lighter. And in this case, both curves show virtually no change until you get up to 2 kilohertz. And then the one that's lighter gets louder and the one that's heavier gets quieter. Both bridges, both violins do the same thing. And in this case, Joseph's actually responds slightly more than mine. I think if you look, the gap between the red and the blue here is just a little wider perhaps than it is here. It also peaks in a different place. He's adjusted his baseline bridge differently. The third parameter relevant to the rocking mode is that length, which I haven't said very much about. So this is the length, the distance from the top of the bridge to the effective center of rotation, the pivot point in my little model. I don't have a really clear grip on how this would vary if you change the actual woodwork in a bridge. That's a story for the future. But somewhat reassuringly, we see rather similar results, this case for the 2 violins and their bridges. They've both got a similar pattern. The blue curve and the red curve trundle along more or less equal. And then in this frequency range around 2, 3, 4 kilohertz, they show just the opposite pattern to the left-hand plots. The blue curve goes up and the red curve goes down. But whereas with the inertia plot, the curves came back together once we got to higher frequencies, but changing this length, the curves cross over and go the other way around. So if you could do a bridge adjustment that changed this length without changing any of the other parameters of the model, then it would make a different difference to the sound.
Jim, could I just ask, would that change be affected by the center of mass of the bridge going up and down?
It's, ask me that again. I've nearly finished here, so ask me that again, because I don't know the answer to that. I mean, it needs thought. Let me just show the other pictures on this, because I think I'm nearly at the end. The remaining 2 pictures show remarkably little. So these are the 2 parameters for the bouncing resonance. This is 30% change in the bouncing frequency of the bridge. And there's a lot of fuzzy stuff here, but the broad trend through the middle of this is barely showing more than plus or minus 1 dB. I'm not sure that I believe these narrow features. I suspect they're artifacts of the computer procedure. So this says to me that there is there is no very striking difference from varying the bouncing frequency by this large amount. Might just be enough to be audible, but it's not going to be very big. It's clearer in Joseph's violin than in mine, but some of this may just be an artifact of experimental noise. The final parameter is a rather similar thing. This is the variation in the bouncing mass. And again, the red and blue curves for my violin, they trundle along really close to 0 dBs across the whole range. So changing that bouncing mass seems to do very little. Slightly bigger effect in Joseph's violin, interestingly. Whether that's enough to be audible, time will tell. But that's as much as I want to say now. I said this was work in progress, and that's absolutely right. I think we're on a promising track here. Nothing has developed far enough that it's directly turned into a workshop tool, but we've got some very encouraging results. And just the fact that we can use this sort of combination of acoustical measurements and computer modeling to say something and to make some sounds to do with bridge adjustment. And we could say something about all 5 of those questions that I asked earlier. This all seems very promising. We just need to do a little bit more. Just as it says here, euphonics.org is my ebook on things. I've been working away on some of this for the last few months, and I needed to do a brain dump. So I'm simply, the story so far has been added into a new section in euphonics. So that's already there, and you can read the story so far. It doesn't quite have everything I've said today. I need to write the next bit, but the intention is that new material will go into there as it becomes available. But with that, I think that's the end for me. So let me stop sharing for the moment so I can see you.
All right. Thank you very much, Jim. So I assume we have lots of questions, so please use the raise hands function.
I could say something about Joseph's question now, just because he got in first. Not in the sense of answering his question, but you have to think rather carefully what those plots mean. That's the first thing, because I've taken 5 particular parameters, and then I'm doing things that you can easily do in the computer, and they're really quite different from anything you do with woodwork. None of those is the effect of carving a bit of wood out of one particular position or adding a certain mass onto the top of the bridge. It's the result of changing the bouncing frequency, shall we say, keeping all the other 4 parameters the same. I have no idea whether you could actually do that. Of course, I could do other combinations of them, and absolutely we could come back on that, but it's sufficiently artificial that it's probably not worth trying to understand exactly what those particular plots mean. The more productive question would be to say, okay, here's something I could imagine doing. So if you actually make the top of the bridge lighter, you probably reduce both the masses together, for example. So, if you think about modeling some adjustment that more like what you might do on the bench, I can run anything through the same process and get a sense of what it means. If you try to do every possibility, you quickly drown in data. So probably we need to have a conversation rather than me giving an answer. Is that fair enough? It's just I wanted to show some sound examples and illustrate the principle of things, but I'm absolutely not claiming that those are sound examples that directly relate to bridge adjustment that you would do at the bench. They're artificial computer adjustments, but I do think that the same process could be used for any realistic bridge adjustment. But what we might need as a backup for that is the kind of thing that we need finite element modeling, probably, if we want to. Either we need a lot of measurements on bridges that have been tweaked in a particular way, or we need a computer model that can relate those model parameters to the actual geometry and the material properties of a bridge. And that's a good question, and Luca has made a start on that, and the people that were at Bielefeld have done a little bit on that, but it's work in progress.
Oliver?
Can't hear you.
Yeah, we're not hearing you.
It doesn't think you're muted, but in fact, I can't hear you. Mute and unmute. Sometimes that makes the audio come to life. Your microphone is not hearing you.
Is that working now?
Yes, we
Okay,
have you.
good. Sorry, I think I have a sound system set up. But yeah, first of all, thank you. That was awesome. Super, super understandable. And it's nice to see it all explained like that. I just had a question about the measuring of the bridge admittance at the points on the violin. Because I noticed that you measured, or you explained, you measured them with accelerometers, and then you hit on the accelerometer with the
Yes,
hammer.
so that's not the bridge admittance. This is the body.
The body
admittance. The body admittance. Yes.
Yeah.
Yes.
Okay, so I was just wondering, is there a difference between the body admittance with a static load at those points that mimics the strings, or is that something that doesn't need to be included, or are you including that with like an offset or something like that?
You're absolutely right to raise that. The fact that that's certainly, I am not including it. I don't know how to do that. The down bearing force will, change the tightness of the sound post and modify the geometry a little bit. And that is absolutely one of the factors. When I said everything is approximate, I don't claim that anything is exact here. And that's certainly one of the factors that's missing. The fact that we can achieve a decent fit suggests that it's not a really big effect, because if it caused a disaster, we'd have been aware of it. It's not so easy to see. Well, no, there are various ways one could try to address that question, but none of them is perfect. You can't measure. The measurement at the bridge feet positions is surprisingly sensitive to being just exactly at the center of the bridge feet. Moving a couple of millimeters in any direction makes a difference that is big enough to matter, which means that it's got to be, you can't get to that place without taking the bridge off.
Yeah.
It's certainly on the list of unfinished business, and I certainly want to go back to that. It's not the only thing that's missing. The strings. I'm not taking any account of strings. So the bridge admittance is measured with the strings on but damped. The body behavior is measured with the strings not present at all. The bridge properties, if you try to measure them independently, are just the bridge on its own with its feet clamped in a vise. So we've got the strings, certain effects of the strings present in the admittance measurement and not in any of the other things. Does that matter? It's a good question. So the down-bearing force is one of the things which could affect the body. The strings, there's a less obvious but probably more important effect of the strings, which is because of the geometry of a violin, where you've got that break angle over the bridge. If the bridge is moving, rocking or bouncing or something, it has to, if you think a little bit about that, if the G string corner of the bridge moves up, for example, then that triangle of G string, if the endpoints don't move, the G string has got slightly stretched by that. So the axial stiffness of the strings acts on the body vibration as a kind of spring stiffness. So that would depend on your brand of strings and what the core material is and all of that. That's an effect which is people have talked about for years, but there's not all that much actual data on it. And say it ought to make a difference. For example, if you have a solid steel E string, would be quite different from a nylon cord metal overwound, dominant string or something like that. Sorry, fan, wrong brand. But so that could be a factor. Both of those things, the down-bearing force and that effect of the string's axial stiffness, are not in my model as I have it at the moment. They're on my backlist of things that at least I know they're not there. So they're known unknowns in the famous phrase. But you're quite right to say, does that make a difference? And the answer is, I don't know, but I have hopes that it can't make a huge difference, because we achieve quite a decent fit just by ignoring those completely. And that must surely mean that it's not a 10 dB's effect. It might be a 1 dB effect, but
yeah,
it's a job for the future.
I wonder, I mean, I don't want to go too much about this, but I wonder if there was a way to put like a non-reactive force in your model and just have like an offset to
the or for the static load.
Yeah.
For the, I mean, that bit of the model is just a direct measurement on the violin. What I would need is to measure those bridge foot positions with the static load in place. Right. That's really difficult to do. The model is only for the bridge itself. Now, the compressive force through the bridge itself from the string load, it would make a big difference if we were looking at out of plane bridge vibrations, bending vibrations. But the simplest theory says that factor shouldn't come in at all to in-plane rocking and bouncing resonances. So in terms of the bridge model, it shouldn't come in. Say if we were thinking of out of plane bending modes of the bridge, which are there as well, they will be affected by that string load. But it doesn't. But it's not really something that the thing that's missing is not in the modeling part; it's in the measurement part. If you can think of a good way to do it, let me know.
Okay, will do. All right, thank you.
Hey, Anders.
Hi, yeah, it's always interesting to see your talks, Jim. And I'm sure if Erik was listening, Erik Jansson, he would smile over this and see that there's been quite a bit of progress since he worked with the bridges and added mass and so on. And I guess you know that he put a stiff bridge on a Stradivari violin and saw the bridge hill still.
Yes, absolutely. That's why I made that filled-in bridge with the cutouts filled in. I think he didn't do the whole story on that, but he did a particular measurement and saw very little change. That's rather extreme, and we've done quite a lot of this sort of thing since. I mean, basically the bridge, either for rocking or bouncing, the bridge is kind of in series with the behavior of the island area. And if you have a connection in series, then the weaker of the two will always dominate. So if the body is very flexible, which maybe a Stradivarius was rather thinly graduated and quite flexible and responsive, then the simple prediction would be that it might be rather insensitive to bridge adjustment. My amateur-made violin, which is probably a little more solid, it's certainly a good deal less valuable, looked as if it was somewhat more sensitive to bridge adjustment. But that experiment with the actual different bridges, you fit those 3 bridges to any violin and they certainly sound different. There's no doubt about that. So and it's not just the mass and the mute effect. I mean, that's what came out of those sensitivity plots. The effect of the bridge inertia and the effect of the rocking frequency are somewhat similar. So in magnitude, by the look of it. So yes.
I have a technical question related to the admittance curves you made. You had the admittance from the violin, and then you had admittance or a model of the bridge. And how do you combine those two? Is it a convolution?
The sound files are made by convolution.
Okay.
Yes. Yeah. That's I get a combined frequency response from the force at the G string notch to the sound at the microphone. I inverse FFT to get an impulse response. I clean it up a little bit and then use that in convolution with the measured string force.
Okay. Thank you very much.
Other questions? What? Aha, okay, Svil.
Hello, thank you very much for this talk and for making it available on your euphonics site. I'd like to reflect a bit about this distance of the top of the bridge to the point of the center of rotation that affects the inertia plot. I've been asked to convert 2 cellos into Baroque cellos, which means putting on Baroque bridges. Who they have a different ratio from the top of the bridge to. Can you hear me?
Yes. Yeah, no, yeah. Absolutely. I can tell that you're about to ask a difficult question. Cellos are a big topic that's on the back list, and basses, if there are any bass people here, they have the same kind of bridge design. A cello bridge with its long legs has a 3rd important resonance where it's kind of sways on the long legs. That's been known for a long time. That goes back to the original measurements on bridges. Evan Davis gave a talk in this series a little while back where he talked about cellos, and he pointed out a possible consequence of that 3rd resonance. Curiously, although I say it's a 3rd resonance, and that might make you think that it's the highest frequency, but it's actually the lowest frequency of the 3. So the first thing that happens with a cello bridge with clamped feet is this swaying resonance. Then it has a bending one, then it has a bouncing one. There are sketches of all 3 of them on euphonics. It looks tentatively that there's been very little work on this. And part of the reason for that is that there is something I'm puzzled by, which poses a measurement challenge. Evan pointed out in his talk that it rather looks as if that swaying resonance of a cello bridge does indeed produce another Bridge Hill-like feature. But that is a little surprising from a physics perspective, because I was already talking with the violin, but the relatively squat violin bridge, I said the main thing it does is converts lateral forces at the top into vertical forces at the feet, and vertical forces are the obvious way to make the instrument body vibrate. that swaying resonance of the cello, I'd have thought the main force of the feet that creates is horizontal rather than vertical. So do you get, maybe there's some, and that might need some detailed modeling, but does that or does that not create much vibration in the cello top? That's a good question. What is needed is a very tricky measurement, because I measured the response on the violin body by tapping with a hammer just normal to the surface on the 2 foot positions. But just as there was a matrix, a 2x2 matrix of admittances for the 2 bridge positions, well, if we want to deal with the horizontal component of force from the feet, then actually at each foot position, there are 2 directions of force and 2 possible directions of motion. But it's really difficult to do the measurement because you can't tap in the middle of the plate in the in-plane direction. You could only think of doing that measurement by sticking a little block on the top, I think, so you could tap that. But then it sticks up above the surface and it will cause some rotation, and that's a slightly different effect. So it needs a bit of, there's an interesting measurement question, and I would like to know the answer to it. One of these days when I'm feeling keen, I suppose I will glue a little block on the foot positions on my cello and try doing it and see what I get. But I haven't yet dared to do it because I would not
I
want
think
to.
George Topani has done it. Thank you very much.
You may, okay, yeah. I mean, you're right that that's a good question, and say that the questions are very reliably raising issues that I knew I'd glossed over, and I do already have on my backlist. That at least is something. Yeah, George is going to ask something anyway. It may not be that.
Can I do it now? Are you ready?
Yeah, go ahead, George.
Yes, thanks for the talk. Well, actually, I believe that you can see that swaying motion in violin bridges, and it's unlike the rocking and bouncing. It's actually visible in the in situ measurements of the bridge. That might mean that it's not actually interacting with the behavior all that much.
Exactly. That I think. No, you sent those pictures, and I think I absolutely agree with you that suggests the exact thing that I was guessing, that it doesn't drive the violin very much. The feet behave more or less as if they were clamped in the vice. But for the cello bridge, there is much more motion with those longer legs. And at least if Evan's guess is correct, then it does seem to be producing a hill. If it's not, then it just doesn't matter. But well, it would affect playability, I suppose, because it would affect the admittance, come what may. But whether it affects the
side of the F hole.
Sorry,
couldn't you tap the side of the F hole and
yeah, I wondered about that.
Vertical motion at the instead of a block up, which is towards the sideways on the island.
Yeah, I did. Yeah, you're quite right. It's what you can't quite get into the right place, and it's not quite the foot position, but it will be something. Yeah, on a cello, there might just about be room to get in. No, it's true. It's a thing to try, but what we've found with again, this might be easier on a cello in all sorts of ways because the frequencies are lower. On the violin, we definitely found that these bridge foot measurement positions, Joseph did a scan across the top at 2 mm spacing, and surprisingly rapid variations just in the radiated sound as you tap, several points across the width of a violin bridge foot. So that was in keeping with what I'd found with just measurement repeatability. So, it's millimeter accuracy. So being on the edge of the F holes is quite a long way away relative to that. But maybe in the in-plane direction, it may not matter all that much. That could be true. Yeah, I'll try it.
Is that something for the wire break? Because you could quite easily sort of stick that under the bridge. And
that's a good question. I'll try that. Yes, all right. I'll just make a note of that. Yes, you're quite right. Wire break.
So
Yes.
I'm going to jump in here for just a second. On the hills we identified with the cello, we were cautious, much like the Bridge Hill original work, is we're seeing a correlation, but we're not really arguing that we have a causality here. We're just finding that those bridge rocking frequencies are lining up with the hills, and some of Jim's work on the center of rotation shifts were also correlated with these different little features here. So
Indeed.
cautious note.
Yeah, no, quite right. But it was an intriguing suggestion, and if it's true, it could be a significant thing. I mean, it would suggest that in bridge adjustment on a cello, you've got one more degree of freedom to play with.
I agree with you, but we haven't proved it.
No, absolutely, absolutely.
Can I ask my question?
Yes, yes.
But before I do that, I'd like to point out that the 3D laser measurements done for the Strad 3D stuff shows a great deal of in-plane motion in the plates. So I mean, the idea that they just move up and down is clearly wrong. Clearly,
yes,
around, but it's not that detailed. I mean, perhaps for the kind of things we're interested in for the bridge at quite high frequencies, possibly the resolution of the measurements isn't high enough, but I don't really know that. But the question I wanted to ask was just a tiny little clarification in around about your last or penultimate slide. You're showing these pairs of violins, yours and Joseph's ultralight. I think in the first one you showed one change and you said what the different colors represented. But in the other two, I think you changed the mass, and another one the height or the length of the bridge. Yeah. You didn't say whether the red or the blue represented an increase or decrease.
Oh, it's all the color code's always the same. The 30% increase and 30% decrease in whichever parameter is being looked at is always the red and blue. So okay. Red, yeah, it was always the same way around.
Okay, that'll do. That's all I needed to know.
And I can show it again if you like, but
yes, just to remind me, because I was trying to work out which direction, say making the bridge taller might be taking us. Although I know we can't.
Well, it's not making the bridge taller.
Well, okay. Well, that would be a factor, but I mean, okay,
no, so it wouldn't. It wouldn't. Well, if you made the legs longer, it wouldn't even make any difference. It's the effective center of rotation of the rocking resonance with clamped feet. So it's where the top of the bridge is rotating about, and that's really hard to guess. Yeah. It's so somewhere in the middle.
Bridge geometry would have changed that effect.
Yeah, that's right. But actually, so I will just hold the bridge up. Where's the camera? Yeah, so changing the height by making the legs longer will make no difference, I think.
Well, that's not the only way to change the height of the bridge. I mean,
no, indeed. No, but then if you make it higher above the heart, you're also increasing the mass. Yeah, it's where, the bridge bending involves flexing at these narrow bits and probably also in these legs here. And the effective center of rotation is presumably somewhere in this middle region, but where exactly at the millimeter accuracy level is pretty hard to guess.
Well,
and indeed, it's pretty hard to measure as well.
Measurements of bridge in situ would probably answer that question. But can we just look at that slide just to refresh my memory?
Yeah. Do it. Show the slide. And go back one. So this one. So this was the first one. This is varying the rocking frequency, and always blue curve is 30% decrease, red curve is 30% increase. So if we now do, so this is rocking inertia. So blue, red. It must be the same. All right. Let me just put the pictures up and show things. I think the code is why it gets louder when you make the inertia higher. All right, you're making me have second thoughts about this. Ask me offline about this one, because I would.
Okay, yes, I was a little bit puzzled.
Yes, it's. I just don't have it. Where is the right window? I would just check the code again to be quite sure what I've done. I mean, it's a matter of reading what the code does, and I'd thought that I've done exactly what I said, but I'll check it out. I haven't quite digested those results. Those were only done a couple of days ago, so they haven't got into the euphonics section yet. They will do in due course, and for that, I will explain them more carefully and think a bit more about them.
Thank you.
Jeffrey?
Thank you. So I just wanted to go back when we started talking about cello bridges, that you have one additional complication for cello bridges, or even more than one, which is Belgian bridge versus French bridge, which I imagine, since you're talking about the that swaying, that the Belgian bridge legs are much longer, and I would imagine have more flexibility, and it's probably for that reason that the ankles of French bridges are lower than on Belgian bridges, which I assume might have evolved to give a little bit more strength to the bridge, to the legs on a Belgian bridge.
Yeah, absolutely. This is. I would love to extend the modeling to include cellos. I just need to be clear about this business about forces at the feet, and what body response is necessary to stir into the model to get some results. But I mean, in general terms, it's always easier to do measurements on cello bridges than on violin bridges, because there's a bigger target to aim at. It's easier to tap in different places. Everything is easier on a cello. And I have one here. I don't have a bass to hand. So yeah, it's definitely on my list to do that. But it does, I need some sense of, if I need to extend the model to include forces in other directions, then that's a different kind of complication. It's all straightforward in principle, but it all takes time and needs data to back it up. So it's a really interesting question that's on the back burner.
Slightly related to that, but slightly off topic. I've never been able to get an answer from anyone that I've asked. When did the terms French bridge and Belgian bridge evolve or were invented? And does anyone have any historical data about that?
Wrong podcast.
It seemed from looking at antique bridges, Belgian bridge styles were around a long time ago, but I don't suppose anyone called them Belgian bridge.
Both have historical antecedents.
Yeah.
But exactly when those names were applied to them, I couldn't tell you that. No idea.
I've not found anyone that can answer that question.
Anders?
Yeah, about the Baroque violin bridge, doesn't it have longer legs? And it probably was a Baroque bridge on the fine old instruments up to whatever, 1800 or something. Is that something to look into? And
historical questions, I'm not at all the person to ask. Yeah, I mean, I could repeat the measurement. Yeah, I could do the test. No, absolutely. Now, if someone would care to fit, well, either lend me a violin with probably a Baroque and a modern bridge, fitted to the same violin, so we measure both and compare and contrast. I mean, I think the same model is going to work. It just that the parameter values will come out different.
Yeah.
And
you know the Hardanger fiddles have two long legs, somewhat similar to the cello, and it has a flat cross section over the top and a central part of the top, and still you have a hill a bit lower than on the violin maybe, but it's still a hill there. I just mentioned it. And then I wonder about maybe I can do some measurements myself if I get some help from you.
Well,
but I have also a question about tops, because you show data from your own violin from 1990, and I wonder, was that a violin under the supervision of David Rubio with a tuned top and thick central part and thinner in the regions upper and lower?
No, it's a violin made in Juliet Barker's evening class.
Okay.
Back when I was, it was my third or fourth instrument, something like that. But it's just an amateur-made Strad pattern.
Yeah, but
isn't too bad.
Is it normal thickness in the center, or is it thickish, or whatever?
It was what I was told was normal at the time, because that was before we saw all these reverse graduation maps and all of that. I think that came after that violin was made. So yeah, I expect it's three millimeters ish.
Okay, a little bit on the thick side then.
Yeah, it wouldn't that, and which is probably why it's more sensitive to bridge adjustment for the rocking frequency. But yeah, amateur classes encourage you to play for safety, you know.
It's not bad to have made several violins, I guess. So
that's a really nice violin, actually. Jim's being modest. It's a lovely violin. We did at Oberlin some years back a comparison between Baroque bridges and normal or modern ones, where we got a model based on, I think, the Stradivari one, the ornamented one, and then a kind of a normal modern bridge, and same material, same mass overall, within a small, very closely matched. What we found was, unsurprisingly, the Baroque bridge is going to have a much higher rocking frequency because the waist is higher up, so there's less mass up there. And without doing anything, it comes around 5 kilohertz. And it really, to me, explained why we moved away from that. It just doesn't put the resonance where we want it. And the difference in sound was more brilliance, more treble output with no loss at the bottom for a modern bridge.
That makes sense. Yeah.
Jim, the swaying mode. Let's say you have a swaying mode. With a cello, I guess it'd be lower. Is that in some sense siphoning energy away from the rocking mode? I know modes don't interact, but what's the sort of?
No, it's just another mode. I mean, the mode shapes have to take account of each other in order to be orthogonal. That's a technical thing. So yeah, there would be. It depends what you mean by interact. Therefore, the mode shapes always, in some sense, have to take account of each other because they have to be. There's a general property called orthogonality that says that you can't have two shapes that's too similar. Basically, if you multiply them together and integrate over their structure, you always.
But they're driven by the same string motion.
Oh yes, no, the excitation.
So it's taking away when you play.
Well,
it's not making sound; it's going to heat.
Well, maybe. Although if it does drive the top enough to create a hill, then it must be driving the top enough to make sound as well. So.
Oh yeah.
if
Yeah,
the
yeah.
hill that Evan saw is connected with this mechanism, then it is probably significant for something. But we just don't know enough yet. It
I
needs
thought
another.
the question was different, that if there is motion without making sound or
Oh yeah,
inefficient
then
making sound, it's taking away.
then
It's an orthogonal mode of the bridge, but it's being driven by the same energy input.
that is true.
That's what
The
Joe
most amusing example of that, in a few years ago, I did some measurements on vials of various designs from Murray Campbell's collection. And so the earlier vials don't have soundposts, and later ones do have soundposts. And one of the things that emerges from it is kind of obvious in retrospect. If you have something without a soundpost, you have a resonance, which I guess it's a kind of version of CBR. The bridge can rock on the island area in a symmetrical way, not constrained by having a soundpost under one foot. So that makes a huge peak, which creates a huge wolf note without making any sound. So it gives you the worst of all worlds. And my one guess as to one of the ingredients of why they took to fitting soundposts in the later vials, the earlier vials, they didn't play that high up in frequency. They only played in first position. When the players wanted to move higher up, on those old instruments, they will have hit this truly wonderful wolf note that makes the note unplayable without being loud. So there's no payoff for it. So putting a soundpost in tames that, and at least means you get some sound out for the price of your wolf note, which is the thing you're familiar with in the cello.
Anders?
Yeah, I was wondering about it's about a side topic, sort of. It's the sound radiation from plates, and George Bissinger, he writes about the radiation efficiency of violins and tries to figure out where it is and so on. And I know you have been working with sound insulation for double walls and so on, where the radiation efficiency peaks around 2.5 kilohertz for gypsum plates and so on. So I wonder what you think about the significance of the radiation efficiency of a closed box like a violin, Jim?
Yeah, that's a difficult question. Evan gave a talk about this, didn't he? I would ask him. He's much better on this kind of sound radiation stuff than I am. I always avoid using microphone measurements on all possible occasions and stick to mechanical measurements. But yeah, you're right that there's a question. I'm skeptical of some of the things that George Bissinger says on that subject, but I'm not going to amplify on that here, I think.
Oh, okay. You don't think it's a significant part of the...
Oh, I'm skeptical about some of the detailed things that he says.
Okay.
Mainly that I think it's more complicated than he claims. And that means that there are no short, snappy answers. There are no single parameters that capture everything.
No.
It's all rather messy, as you know, really. But yeah.
Well,
Okay.
not really. I'm not sure whether it's related, but if you measure the radiation at the bridge feet, and you just sort of put both bridge feet together, so it's not really a measure of anything, but it gives you a sense of what the violin's doing over its frequency range. And I did one of those in Cambridge and showed it to Jim, and Jim just took the frequency range right up to Nyquist frequency, and yes, it just radiates in a straight line. And then as soon as you put the bridge on, of course, so all of this notion of, it seems like on its own, the violin is perfectly capable of, playing for bats, or, it's everything else happening with the bridge.
Yeah, that's probably right. And if you if you could string your violins in the way that the Chinese erhu is strung, where you bow the string vertically, you thread the bow in between the two strings. That means you're driving the string. Then you don't need the high bridge and the cutouts and any of those things. You can have a little squat bridge, and that has a very piercing sound. But then they use a membrane for it. But as you say, it's the bridge, the mass, and to some extent these resonances that give you the cutoff that rolls off the really harsh high frequencies. And that is the main thing probably that you're doing in bridge adjustment. But it's more interesting than that. That's why I thought those difference curves are quite interesting, just to bring out which frequency ranges are going up and which ones are going down. But if you didn't have to convert that transverse force into vertical forces because you bowed in a vertical direction, then you wouldn't need a bridge. You just need a little sort of scrap of stuff. And then you wouldn't have the mass and you wouldn't have the resonance, and it would probably be very harsh.
You'd need a hole going right F-holes in the back too.
Yeah,
so
it's hard to do with 4 strings to do the erhu trick, yes. But yeah, that's probably fortunate.
What do you think the significance of a soft versus a stiff bass bar is on the bridge response, or the total response of the violin?
Joseph gave a talk about that. Rather small, I think, was the conclusion.
Okay.
Bass bar. We've had a couple of talks about the bass bar project, haven't we?
Yeah, and there should be an article coming out in Strat, I think in July, now, which summarizes it. And it showed that the kind of normal 12 millimeter down to the under 4 gave the most sound output in all frequency regions, and then you start losing. It depended on the instrument, but well, it does make a difference, and it suggested to keep doing what we're doing. Maybe a little more scoop help in some cases, but I would love to see at some point Jim put that into his bridge model, although of course it's maybe not feasible to do, just so we could sort of have all the knobs that are at our disposal.
Yeah, that would need one of the finite element people. You need a different style of model altogether. My mass and spring as an individual modes is far too simplistic to capture that kind of thing.
Well, if I can just say, I'm looking forward. Luca's here right now, and we're trying to pursue in much more detail the bridge foot radiativity, how it relates to the bridge foot admittance, and we just put, for example, a solid bridge, so there's no resonances, and it's absolutely fascinating. And from a number of points of view, it seems as soon as you put a bridge on, you lose a bunch of stuff you probably can't get back unless there is some radical design change, which I don't know how to do. But also this issue of exactly where the bridge foot should be, it's extraordinarily sensitive, as Jim was saying, both in admittance and radiativity, and we're going to try and map that out. But it may be the case that one needs to prospect for each instrument. Where is the best place to put the bass and the treble feet? Why should they all be, 41? Why should they be symmetrical? I don't know whether the variations we see are general across the range of violins, or they vary a lot, or they depend on the details of where the bar is, in particular the bridge foot. And then also going north and south, especially on viola, I ask, what's the ideal string length? And you get into geometrical arguments, but there's no reason to think that they hold any water acoustically. And I don't know, as a maker, it's a frustration. You only know what to do with the instrument after you've got a bridge on, and by the time you put the bridge on, you made a whole bunch of decisions. So the underlying project for me is, how can we characterize an instrument just by measuring the bridge foot admittance. So without strings, it'll have to have a post in. And can we do that without the neck on? At what point can we get a good enough sense of what the instrument's doing, what it could do with any possible bridge, that we could then make an intervention before we, put too much more time into it. So let's stay tuned. It may be a month or two, but there's a lot more in this project than Jim has. Well, Jim's given a brilliant start to all this, and I thank him again for it.
Yeah, so on that note, let's end this section and give Jim and the whole group, experimental group, a great round of applause.